Today we're going to talk about circuits. Circuits are a closed path for current that can flow. So they're generally consisting of batteries, wires, resistors, and switches. Hopefully you have an idea of what this is outside the class. If I take a wire and I connect a battery and maybe like a flashlight to it, I can make that flashlight light up because it's getting power from the battery. Okay, we talked about last time that the current is always going to flow from high potential to low potential. Today we're going to talk about circuit diagrams. So how do we sketch circuits and how do we draw them? And then we're going to talk about some calculations we can do with them. Just keep in mind, if you look anywhere else online for notes, they might use slightly different symbols than me, but they should look similar enough and they should be labeled. And so I'm going to just make sure that you know that other people's symbols might not look exactly the same as mine. Some general circuit symbols. Resistors look like this. I'm going to keep moving on, so pause the video when you need to for each slide. Voltage sources look like this, so like your batteries. And remember, positive to negative. And remember that it says charge flows from negative to positive. Charge does. The actual electrons do, but we say the current flows in the opposite direction. Current actually goes from positive to negative. And then we have conductors, which are straight lines, and so all these straight lines are conductors. And then switches look like this, just little dots. And it can be open or closed. Again, open means that there's no power, and so if a light switch is off, it is open. And if it's closed, that means it's on. And so we can label a diagram like this. We have a switch, voltage source, and a resistor, all connected by a wire going throughout. We have two devices we can use to measure current and voltage. We have a voltmeter and an ammeter. Voltmeters, they measure voltage, and they do this by having a very, very large internal resistance connected into parallel. We'll go back through this slide after we have an understanding at some point, after we go through all the circuits, maybe next class, so you have a better idea of why all the notes here are the way they are. But you just need to know for now that they have a very large internal resistance and they're connected into parallel. Those are just facts. What those mean and why they are the way they are, we'll get to later. And then ammeters measure currents. They have a very low internal resistance in order to do that, and they're connected into series. And so mainly just look at the diagrams. Since this is parallel, it's saying it's in a separate loop. There's now two paths here, 1, 2. They're separate paths that the current's flowing through. But here, there's one path that the current flows through. That means it's connected into series. We're going to start with series circuits. Series circuits are single loop circuits. We have certain rules for them. Again, I'm going to let you just copy down this slide, copy down the rules, and then we'll talk about them as we go through an example, and it's going to make more sense. So just copy them down for now. So here's the example. Here's a circuit here. We have a voltage source of 18, and we have 3 resistors, 25, 35, 32. And some questions we want is we want to find the total resistance. We want to find the current in each resistor, and we want to find the voltage drop across each resistor in this circuit. Okay, so how do we do that? So let's talk about what this actually means. So in a circuit, we have a power source, and it gives 18 volts. And in a series circuit, what that means is that every resistor is going to do something called a voltage drop. It's going to take some of the voltage away as it goes through. And as it goes all the way through in series, the voltage drop is going to go to 0. So as maybe it drops maybe like 7 here, maybe like 8 here, and then maybe like 3 here. And that should add up to 18 if you do it correctly. Those are not correct voltage drops. I'm just giving you an example. We'll actually calculate this here in a second. Okay, what the actual answers are. So every resistor has its own voltage drop. Every resistor has its own current flow. The current's going to go through, and we can calculate the amount of current for each resistor. And then each one has its own resistance, obviously. There's also an equivalent resistance. So we can calculate all the resistors as a whole. What is their overall resistance? If we have them as if it's one resistor, what is the resistance there? What is the total current of the series? And then what is the total voltage drop, which we know is 18. It's given to us. To do all that, we're going to organize by using a T-chart. We're going to have and I call it a VIR chart, because at the top we see VIR, and we're going to find the voltage for every resistor. We're going to find the current for every resistor, and we're going to find the resistance for every resistor. We can fill in some of these for free. We know the total voltage is 18, and we know our resistors are 25, 35, and 32. And we can use this information to solve the rest of the chart. Remember our rule for resistance. Let's go back. Total resistance is the sum of all the resistances. So my total resistance is just adding this up. 25 plus 35 plus 32. 92. Okay, so if we're doing columns, we're going to look at the rules. So columns, rules. If we're doing rows, we know V equals IR. Whoops. V equals IR. Okay, so voltage is 18, and my resistance is 92, so I'm going to divide by 92. And you should get a current of 0.196. And guess what? That's the same current throughout the entire thing. So I'm going to multiply. So I'm just going to copy and paste it because the current is the same in every part of the circuit according to that rule. So again, if you want to fill out columns, you look at your rules. If you have enough information in the rows, though, like we now do again, I have enough information in the row to fill out V. V equals IR. So I just multiply my current times my resistance. Here, 25 times my current. And I'm going to use the non-rounded current. It gives me 4.89. 35 times my non-rounded current is 6.85. And then 32 times my non-rounded current is 6.26. And that should add up to about 18. Obviously, when you're round, you might get a couple decimals off, but you should get the same voltage about approximately. I'll leave the second example practice for you to do. And there's the answers if you get them correctly. For parallel circuits, we have a new set of rules. So what is a parallel circuit? A parallel circuit is when there's multiple loops. And so as you can see here, we have one loop here and we have one loop here. Okay? The current, when it goes through, it's going to go from positive to negative. So the current's going in the right direction. It's going to go, and it's going to split paths. One path goes this way, one path goes this way. And so the current is going to split in a parallel circuit. And so here are the rules for parallel circuits. Voltage drop is the same. So every single path gets the same voltage. The current splits, which means that the current is going to be the sum of all the currents through each leg. And then the resistance is actually just going to have a special equation that I'm going to show you. This is the equation. And it's not filled in, so it's 1 equals R is 1 over R1 plus 1 over R2 plus for as many resistors as you have. So to get the inverse of the resistance, you add up the inverses of all the resistors. So I will show you how that works whenever we do the example. So let's look at this. We have a 45 volt resistor and we have two resistances, 85 and 35. Let's find the total resistance, total current, and the current through each leg. And I'm going to go back to that slide to do it. So 45, 35, 85. Hold on. Let me write that down. 45, 85, 35. Okay, I'm going to go back to that slide so I have room to work. Here we go. And I will erase. Whoops. Why is it not working? It's not wanting to clear. Let me just close out, discard, and go back in. Okay, so my total voltage was 45. My current, which I don't know, but I know my resistors are 85 and 35. That should be an 85. And then we're going to ignore this third one because there's not a third resistor. So we only need 3 rows here. How to find my R? I know that 1 over R is equal to 1 over R1 plus 1 over R2. And you keep doing that for how many we have. We only have 2, so we're just going to leave it like that. If you had 3, you would do something like this. And if you had 4, you could add a 4th one on. And if you had 5, you could add a 5th one on, and you could keep going. But if you only have 3, you only do that. We only have 2, so we're going to do that. So in this case, we have 1 over 85 plus 1 over 35. 1 divided by 85 plus 1 divided by 35. That gives me some decimal, 0.0403. That's cool. That's not your answer. Don't stop there. That is 1 over our answer according to the equation. And so we need to do 1 divided by this number in order to get our actual resistance. So 1 divided by that answer is equal to 24.8. Okay. Then to get our current, we know V equals IR. From here, it's about exact same as last time, except for we had different rules. So to get our current for the whole thing, we get 45 divided by that resistance. And I get 1.82. And then our voltage, we know based on our parallel rules, which you should have copied down, the voltage is the same through each leg. And so I can copy down this voltage for all of them. And then now I know V equals IR. So I can find the current each one. 45 divided by 85 is 0.53. And 45 divided by 35 is 1.29. Which this column should add up to 1.82 if we did it right. So 1.29 plus 0.53, which does give me 1.82 back, so I did it right. Again, if you round differently than me, you might have a few different answers. You might be off by a decimal or 2. That's okay. As much as possible, try to be as accurate in your numbers as possible. Try not to round using your calculator. Okay, and so again, there's another practice one here that you can try to do. Here's the equation and kind of the steps to how to do it. And then here is the picture if you want to see a sketch of a parallel circuit. And then there's different ways to sketch them, just so you know, but here's one way to sketch it. And that's it for today. So next time we're going to do complex circuits where we mix up series and parallel. We're going to put series into parallel circuits, and we're going to parallel into series circuits. And so they'll be a lot more mixed up. With that, have a good day.